Hello and welcome to this video. In this video, we will learn about open addressing in hashing. So as we had discussed, there are three methods by which you can achieve open addressing. One is linear probing, second is quadratic probing, and third is double hashing. So we will use double hashing as a mechanism to perform open addressing. So in this, I have a global prime 11. This should be less than the table size. So we'll go through the program in a bit. First, I must welcome people who are new to the channel, and I am very grateful to you guys because I have crossed 500 subscriber mark. So a lot of thanks to you guys for keeping me motivated. If you are new to the channel, make sure you subscribe to the channel and press the bell icon so that you can get notification about more upcoming videos on data structure and other playlists which I make, like Rust programming or Python programming or class 12 maths, and spread the word around with people around you who can benefit from my videos. So let's get back to the program. So our prime is 11, which should be less than table size. I have made the table size 13. I declare a variable array which is of the table size. Keys present, that is number of values present in the hash is 0 to begin with. I initialize the hash table with hash table and table size. So basically I mark all the entries -1, that is values are absent in this. -1 represents absent value, -2 represents deleted values. After that, I insert 115, 12, 87, 66 and 123 in the hash table. So I pass hash table, table size, because arrays degrade as a pointer, so I need to send the size of the array, keys present and the value to be inserted. So how insert works, you actually already know if you are following my videos. So if value is -1 or -2, it cannot be inserted. If table size is equal to keys present, that means table is full, so we return. If that is not the case, if these two are not the case, then we calculate the probe. So probe is simple value percentage table size. It is the same as the previous video on separate chaining. So this is the first modulus function which determines the probe. And the second hash function which I have chosen is prime minus value percentage prime. So this gives us our offset to this. So if a collision occurs at probe, we add offset. We check that value. If collision occurs at that, we again add offset, and that's how we cycle through all the cells. So a good hash function should be able to cycle through all the cells in case of collision. So we check if probe is -1, is not -1, and then we check that probe is not equal to -2. If that is the case, then we break. Okay, if that is not the case, we increase the probe by offset. And then once we have found that at that position, we put the value, we increase the keys present. Now after the insert, the search is similar. You have the probe, you have the offset. First iteration is true. You check probe is -1 or not. You check probe is value, that is we found the value or not. Or you check probe is at initial position and it's not first iteration, then you return false. Otherwise you increase the probe and go on repeating through till you find or return, and eventually you return false if you break out of this. Okay, delete is also similar. You search for the element, you find the probe, you find the offset, and you check if probe is not -1, then you check if it has value. If it has the value, then you set probe to -2, that is a deleted element, and reduce the keys present. This should be star. Okay, you reduce the keys present, and for print it is simple. You just go on printing that. So it's a very simple, straightforward problem if you have been following my previous videos. The only key thing is the second hash function. Apart from this, there is nothing more to this program. It's a very simple, dead simple, straightforward implementation. No tricks, no clever programming, just simple logic. So let's see this in a run, but before we see the run, let's go through the values which we are inserting and deleting. We have inserted 115, 12, 87, 66 and 123, and 1 will not be found, 12 will be found, and 115 will be found. Other values will not be found. We delete 123, 87 and 66. So 12 and 115 will remain. So let's compile this program and run this. Okay. Okay, I will have to remove the W error. So at the end, 12 and 115 remain. This is before the deletion, and this is after the deletion. You see 66, 123 and 87 are replaced by -2 here and here, and 12 and 115 are present as we had seen. So it's a very simple program. There is not much explanation I can do for this. So if you do not follow this video, then I'll recommend you that you go through my previous videos on hashing and go through the theory. Once you go through the theory, this will become very clear to you how this works. So with this, we come to the end of this video. And now that we have finished most generic data structures typically found in a semester course, we will now explore more esoteric data structures. For example, red black tree, AVL tree, tournament trees, and we will see some famous algorithms like maximum subarray problem or Cardan's algorithm and Queen's problem. So those kind of problems we will solve, and we will proceed further into deeper reaches of data structures. So I'll see you in the next video. Please make sure that you like the video, share it on social media, and make use of the comment box to give me feedback or suggestions, or just to talk. If you want idle talk, I can do that. So thanks a lot for watching. Happy programming.